Hi, my name is Akanksha Athre, and I will be talking about preserving privacy in personalized models for distributed mobile services. This work was done with Prof. Prashant Shenoy and Prof. David Jensen at UMass Amherst. The ubiquitous nature of smartphones and smart devices, such as wearables, have led to a plethora of online mobile services in various domains, including entertainment, healthcare, and travel. These mobile services are often distributed between the cloud and end device. Modern mobile services are context aware to provide tailored service to users based on their current context. For instance, a mapping service uses temporal and spatial context, such as location and timestamp, to provide tailored content about location ratings and reviews. More recently, context aware services are thriving not only on using the correct context, but also predicting future context to prefetch content or provide recommendations based on expected future mobile behavior. For instance, a mobile application that predicts a user's next location can provide tailored recommendations regarding the location's surroundings, such as a restaurant's closing time and future traffic predictions. This is generally done via large machine learning models built to support a range of users. However, a recent trend in the field is to use personalized machine learning models on a per user basis to improve the efficacy of the context prediction models. In this scenario, rather than using a single ML model for all users, a model is personalized for each user using training data specific to that user. For instance, users frequently visited locations in the mobile service can be used to develop a personalized next location prediction model. However, since personalized ML models encode sensitive information in the single user context traces used as training data, they can leak privacy. This leads us to the key question: can personalized mobile services be exploited to leak sensitive context information about a user? To assess this question, we first ask how much leakage is present. We then see what we can do to address the privacy leakage. Having presented the motivation of our work, the outline of the rest of the talk is as follows. I will next present privacy leakage from attacks on personalized mobile services. Then I will introduce our privacy preserving personalization framework, Pelican, and finally conclude the talk. To understand privacy attacks in mobile services, let's consider a trained machine learning model. These models take as input some data, such as location information, and output a prediction, such as next location. A simple model inversion uses the output of a machine learning model to infer the input. In case of a next location prediction model, it implies taking a predicted next location, the model output, to learn one of the previous locations, the model input, visited by the user. The key idea is to maximize the model's confidence to determine the best value of the sensitive feature. This is concerning given the sensitivity of location data. For example, a visit to a hospital can leak privacy. The goal is to not reveal more than needed for the service to operate. We propose a time series adaptation of model inversion attacks. Let xt be a sequence of features at time t, and let the model take as input the past two sequences to predict the next location. We assume that an adversary has access to all or no features within a sequence for a given time step. This increases the complexity of the traditional attack substantially due to the time series nature. However, considering that mobile devices are consistently with users, we can assume that there exists cross correlation between consequence sequences and continuity. Thus, we can use smart enumeration techniques that take advantage of these correlations by enumerating through only certain features and using cross correlation to infer the rest. We assess the efficacy of the attack on 100 distinct users using campus scale Wi Fi traces. We compare a brute force method that iterates over all possibilities with a gradient descent and time based method. The brute force method performs well along with the time based. The gradient based method, however, does not accurately reconstruct historical data due to the large domain size, which is the number of locations in this case. However, despite the equivalent performance between the brute and time method, the time based method is 120 times faster. We conclude that the privacy attack is computationally efficient and effective with 77.61% accuracy for top three estimates. Combined with other experiments in the paper, we conclude that context-aware personalized models can be easily exploited with limited information for users with highly correlated mobility patterns. Considering the privacy leakage present in state-of-the-art personalized ML models, we introduce privacy-preserving personalization framework Pelican. Here, gray and yellow represents phases that are executed on the cloud and device respectively. The first step is cloud-based initial training. It trains a general model using training data from multiple users. Then, this general model is used for device-based personalization. A small amount of user-specific training data is used to personalize the model on the local device using adaptive transfer learning methods. Keeping training on the local device preserves privacy as the training data is not exposed to the service provider. The model can then be deployed in two ways. The first approach is local on device deployment, where the model executes on the device for making predictions. The second approach is to deploy the personalized model in the cloud for cloud based services. In this case, even though the model runs in the cloud, its privacy enhancements, as we will see on the next slide, prevent model inversion attacks. Lastly, as new personal data becomes available, the transfer learning process can be reinvoked to update the parameters of the personalized model, after which it is redeployed for use by the service. We now present our privacy enhancement to the model that is designed to thwart inversion attacks. The proposed enhancement is based on modification of the confidence scores such that the attack space reduces tremendously. Before applying the softmax function to normalize raw probabilities from the model, this new layer scales the probabilities by dividing them with a value t, also known as temperature. Intuitively, this makes the attack more difficult because the confidence scores will be highly insensitive, either close to 0 or 1. With less sensitive confidence values, the attack space will reduce. In this work, the user picks this value to be used during inference time and keeps this value private. To evaluate Pelican, we try out two transfer learning methods on campus scale Wi Fi traces. The results shown are aggregated for 100 distinct users. The proposed solution is able to reduce privacy leakage by 46 to 54% for transfer learning methods. As K increases in both types of models, there is less privacy leakage. Furthermore, we evaluate the impact of the value of the temperature on privacy. As the temperature decreases, the privacy leakage decreases, eventually flattening out. Thus, Pelican is able to lower the ability of the attack to the extent that it is incomprehensible without compromising on model accuracy. To conclude, personalized models are capable of leaking private information despite being trained in a privacy preserving manner. This is particularly problematic in context aware applications. The proposed distributed framework Pelican learns and deploys transfer learning based personalized ML models in a privacy preserving manner on resource constrained mobile devices. For more details, please check out our paper. Thank you.